Components such as pins or bolts that connect two parts are generally subjected not only to bearing pressure but also to shear loading. As an example, we consider a pulley. The pulley is mounted to a vertical support by means of a bolt. A chain is placed around the pulley and is loaded with a certain force. The bolt is subjected to shear loading in the cross-section between the pulley and the support. If the force in the chain becomes too large, the bolt would be sheared off at this location. This shear loading can indeed be compared to the action of the two blades of a pair of scissors. Just as a sheet of paper is cut between the two blades, the bolt is cut by the pulley and the support. The magnitude of shear loading on a component depends on the intensity of force distribution over the cross-sectional area, that is, on the ratio of force to cross-sectional area. This quantity, representing the governing load intensity, is defined analogously to normal stress under tensile or compressive loading. In contrast to tensile or compressive stresses, where the force acts perpendicular to the stressed cross-sectional area, the force in shear loading acts within the plane of the cross-section, or parallel to it. For this reason, shear stress is not denoted by the Greek letter sigma, but by the Greek symbol tau. Under shear loading, certain shear stresses in the component must not be exceeded, otherwise the cross-section will start to fail. This limiting stress at which a cross-section begins to shear is referred to as the ultimate shear strength. However, irreversible plastic deformation already occurs at lower stress levels. This limiting stress is known as the shear yield strength. For steels, the shear yield strength can be estimated for preliminary calculations from the tensile yield strength Re. For static loading, it is typically on the order of approximately 60% of the tensile yield strength. For the design of a component subjected to static shear loading, the condition therefore applies that the actual shear stress must be smaller than the shear yield strength of the material. For safety reasons, the maximum allowable shear stress used in practice is significantly lower. The ratio between the shear yield strength and the maximum allowable stress is expressed by the safety factor nu. In practice, given a selected safety factor and a known shear yield strength for the material, the maximum allowable shear stress can thus be determined. By rearranging the shear stress formula, a given external force and the maximum allowable shear stress can be used to calculate the minimum required cross-sectional area of the component. Let us consider the example of the illustrated bolt used to mount a pulley to a support. The pulley exerts a constant force of 80 kilonewtons on the bolt, which is made of unalloyed steel E360. The question is, what minimum diameter must the bolt have to provide a safety factor of 1.5 against shear failure? To answer this, we first need the tensile yield strength of the material in order to estimate the shear yield strength. The yield strength can be obtained from the steel designation E360. The numerical value directly represents a yield strength of 360 newtons per square millimeter. Multiplying this value by a factor of 0.6 yields an estimated shear yield strength of 216 newtons per square millimeter for the bolt material. Using the given safety factor of 1.5, we can now determine the maximum allowable shear stress. This results in an allowable shear stress of 144 newtons per square millimeter, which must not be exceeded in the bolt cross-section. Using this allowable shear stress and the applied force of 80,000 newtons, we can determine the minimum required cross-sectional area. Substituting the numerical values yields a required area of at least 556 square millimeters. The area of the circular cross-section is calculated using the given formula. Rearranging the equation and substituting the values results in a minimum required bolt diameter of 27 millimeters when rounded up. With this diameter, it is ensured that the maximum allowable shear stress of 144 newtons per square millimeter is not exceeded. Let us now consider a further example. In this case, the pulley is mounted between the supports as shown. What minimum bolt diameter is now required to prevent shear failure under a force of 80 kilonewtons and a safety factor of 1.5? At first glance, one might assume that the situation has not changed significantly. Upon closer inspection, however, a crucial difference becomes apparent. In this case, the bolt is subjected to shear at two locations. This does not result in higher loading, but rather the opposite. The bolt is subjected to lower stress because the total force of 80 kilonewtons is distributed over two cross-sectional areas. Each cross-section is therefore loaded with only half of the original force. Consequently, the shear stress is reduced by half, since the force is no longer applied to a single cross-section but to two. We now calculate the required bolt diameter. The shear yield strength and the maximum allowable shear stress, being purely material-dependent properties, remain unchanged. Instead of the previously acting shear force of 80 kilonewtons, we now use a shear force of only 40 kilonewtons per cross-section. Accordingly, only half the cross-sectional area is required, amounting to approximately 278 square millimeters. Using the rearranged formula for a circular cross-sectional area, we obtain a minimum required bolt diameter of only 19 millimeters after rounding up for the double-shear configuration. In conclusion, the most important formulas for designing components subjected to shear loading are summarized once again. As demonstrated, it must be distinguished whether a component with single-sided support is subjected to shear at only one location or, in the case of double-sided support, at two locations. Accordingly, the applied force is distributed over one or two cross-sections. In a so-called double-shear configuration, only half of the force acts on each individual cross-section. This assumes that the cross-sections subjected to shear are symmetrically arranged with respect to the applied force. In this case, the force in the formula for calculating the minimum required cross-sectional area is divided by a factor of 2. Alternatively, by rearranging the formula, the situation can be interpreted differently while leading to the same conclusion. If the factor of 2 is moved to the left-hand side of the equation, the formula can be interpreted as the full applied force acting on two cross-sections simultaneously. Whether one interprets the situation as half the force acting on one cross-section or the full force acting on two cross-sections, the final result is identical.